We use the internet all day, every day. But have you ever really stopped to think about what's going on under the hood? I mean, how it actually works? What feels like absolute magic is, turns out, one of the most brilliant pieces of engineering we've ever come up with.
Just think about it for a second. You make a single click on a link or you tap on your phone screen, and somehow that one action finds the exact right server, which could be thousands of miles away, and pulls back the exact data you wanted. And not just that, it comes back in the right order, all in a fraction of a second. How is that even possible across a network as massive and chaotic as the internet?
Well, the secret isn't some kind of digital sorcery. It's actually much simpler, and in a way, much more impressive. It's just an agreement, a universal rulebook that every single device, from your tiny smartwatch to a giant server in a data center, has agreed to follow. It's this shared language that makes it all possible.
So let's pop the hood and take a look at the blueprints for this global conversation. This is the internet's rulebook.
To manage all this complexity, engineers came up with a brilliant idea. Break it down into layers. You'll see two main models for this. There's the 7-layer OSI model, which is kind of like the detailed academic textbook version. It's fantastic for learning because it separates every little job. But then there's the 4-layer TCP/IP model. This is the streamlined, practical model that the internet actually runs on today. You can see it just combines a few of the OSI layers. The goal for both, though, is exactly the same. Take an impossibly huge problem and slice it into smaller, manageable chunks. And that really gets to the heart of it. This whole layering thing isn't some sacred, rigid law you have to worship. It's a practical guide. It means the person designing your Wi-Fi card doesn't need to know anything about how your email app works, and the email developer doesn't have to worry about radio frequencies. As long as each of them plays by the rules for their own layer, the whole thing just works. Okay, so to really see these layers in action, we need to zoom in on maybe the most important moment of any connection, the very beginning. It all kicks off with this simple, really elegant little dance called the Three-Way Handshake. Now, this handshake is part of something called TCP, or Transmission Control Protocol. And you can think of it like this. If sending data is like sending a letter, TCP is the certified mail service. It doesn't just toss your data into the void and hope it gets there. No, it establishes a solid connection first. It tracks every single piece of data, and it absolutely guarantees that everything arrives safely and in the right order. So before even one byte of your actual data gets sent, this little exchange has to happen. It's super simple. Your computer, the client, sends out a message called a SYN. It's basically saying, hey, can we talk? The server gets it and sends back what's called a SYN-ACK, which means, yup, I hear you and I'm ready to talk too. Then your computer sends one final AK back just to say, awesome, I got your confirmation. SYN-ACK. It's a confirmed hello, and only then does the real data start to flow. But here is the really clever bit. This isn't just about being polite. What's actually happening here is that both sides are exchanging a random starting number. It's called an initial sequence number. Think of it like both sides saying, okay, the first piece of data I send you, I'm going to label it #1. The next will be #2, and so on. This synchronization is the secret sauce to TCP's reliability. It's how they keep perfect track of everything that's about to be sent back and forth. All right, the handshake is complete, the line is open. Now we can finally send the data. But you don't just dump it onto the network. No, it gets carefully wrapped and packaged as it moves down through those layers we talked about. So it all starts with this. Your data. This is the actual stuff your app, say your web browser, wants to send. Right now, it's just the raw content, a stream of ones and zeros. First, that data gets handed down to the transport layer. Here, TCP slaps a header on the front, and this whole unit is now called a segment. And that header is critical. It contains the port numbers, which are like specific apartment numbers for the apps on each computer, and it has those sequence numbers from the handshake to keep track of everything. Okay. Next up, that segment gets passed down to the internet layer. And what happens? It gets another header added to the front, the IP header. If the port number was the apartment number, the IP address is the building's main street address. It's the global address that tells the internet which computer to send this to, anywhere in the world. Now we call it a packet. Finally, for the very last step before it leaves your device, the packet is handed down to the network access layer. Here, it gets wrapped in one more layer, creating what we call a frame. Think of this as putting the addressed envelope into a local courier's bag. This frame adds the MAC address, which isn't the global address, but the specific physical address of the very next device on the journey, like your Wi-Fi router. It's the full, complete package, ready to fly through the air or down a cable. So we've walked through this whole process, the handshake, the wrapping, the headers. You might be wondering, why? Why all the complication? Why does this whole layered system even matter in the real world? Well, this separation of jobs is the internet's absolute superpower. First, it gives us interoperability. It's the reason an Apple iPhone and a Cisco router built by completely different companies in different decades can talk to each other perfectly. They just follow the same rules. Second, it gives us resilience. We can invent brand new technologies like Wi-Fi or 5G for the physical layers, and we don't have to reinvent all this stuff at the top, like email or the web. And maybe most importantly, it sparks innovation. Because the layers handle all the messy, complicated stuff, a single developer can create the next killer app without being an expert in fiber optics. They can just focus on their one little piece of the puzzle, totally confident that all the other layers will be their job. And when you step back, it's pretty mind-blowing. The basic ideas behind TCP/IP were dreamed up over 40 years ago, back in the age of clunky terminals and dial-up modems. And yet that same fundamental rulebook scaled up to build the incredibly fast, always-on world we live in now. It really makes you wonder, if this model got us this far, what will the rulebook for the next 40 years of communication even look like? And what kind of world will it build?